exercise number 1.1. It is given to find HCF using Euclid's division algorithm. So we have two numbers here, 135 and 225. So as I have told you, we have to start with the greater number. 225 is equal to, we all know 135 ones are 135. 135 twos are will be 270. It will be greater than 225. So I'm just using 135 ones are plus 90, because 90 plus 135 is 225. Now we shall write this 135 here. So now it will become 135 is equal to 90 ones are 90 plus 45. In the same way we can write 90 is equal to 45 into 2 plus 0. So finally we got remainder to be 0. So which was the last remainder before 0 was 45. And so we can say HCF of 135 and 225 is equal to 45. Let us do one more question. It is equal to find the HCF of 38,220 and 196. Again we can see the greater number is 38,220. So 38,220 here we can write directly. It is 196 into 195. Okay, it is the exact multiple of 196 by 195, and so that the remainder will be equal to 0. Okay, so 196 itself is the HCF. So we can write HCF of 38,220 and 196 is 196 itself. Like this you can do many more sums. Now let us prove one more sum. Show that any positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5, where q is some integer. Now here let us suppose, because the divisor is 6, right? So we can say let a be any positive integer. If a is any positive integer according to Euclid's division lemma, we know a is equal to bq plus r. Here if you take b is equal to 6, so this will be a is equal to 6q plus r, where the value of remainder will be greater than equal to 0 and it will be less than 1. This shows r will be either 0, 1, 2, 3, 4 and 5. Right? So we will be taking different values of r to know what do we get a. So let us see. Now you can see here, I have already mentioned when r is 0, a will be 6q plus 0, r is 1, a will be 6q plus 1 and so on up to r is 5. Now we need to express in the form 2m or 2m plus 1. So 6q means we can write it is a multiple of 2 into 3q. Right? So this can be written as a is equal to 2m, where m is equal to 3q. We can take any constant number as m. Same way 6q plus 1 can be written as 2 into 3q plus 1, which can be written as a is equal to 2m plus 1, where m is again equal to 3q. So here we got the value of a as 2m plus 1, supposing m is 3q. Same way we can convert this also. We can take 2 common. So this will be 3q plus 1. And so a will be again converted of the form 2m. If you are confused that this m was taken earlier to be 3q and here m is taken to be 3q, so you can replace it by some other alphabet k also. Right? So in the same way, this can be further written a as 6q plus 3. Okay, so we can write 2 into 3q plus 1. 2 3s are 6q, 2 1s are 2 plus 1. That is 2 plus 1 will become 3. So now again a can be expressed in the form 2m plus 1. So where you can take m as 3q plus 1. Similarly, the last two, you can take this 2 common, so it will become 3q plus 2 this time. So a is again of the form 2m, where m is equal to 3q plus 2. Same way, this 6q plus 5 can be written as 2 into 3q plus 2 plus 1. 2 3s are 6q and 2 2s are 4 plus 1 will become 5. And so a is again replaced in the form of 2m plus 1, where m is 3q plus 2. Now out of these 6 results, you can say somewhere it is of the form 2m and somewhere it is of the form 2m plus 1. Now we know that every positive integer can be expressed as every positive integer is of the form 2m, and therefore every odd number, so if I am talking about every positive even integer, it will be 2m. So every odd positive integer will be of the form 2m plus 1. And what was 2m plus 1? If you can see properly, so we were having a is equal to 6q plus 1. Here 2m plus 1, a is equal to 6q plus 3, and 2m plus 1 is a is equal to 6q plus 5. Right? So therefore we can say that it is proved that any positive odd integer is of the form 6q plus 1, 6q plus 3, or it can be 6q plus 5. Okay. Now our next question is, an army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? Now if you want to know that how many columns are there, so we will have to find out the HCF. HCF of 616 and 32 will give you the maximum number of columns. So as 616 is the greater number, I can write 616 is equal to 32 into 19 plus 8. Same way, 32 will be equal to 8 4s are 32, so the remainder is 0. And thus we can say the HCF of 616 and 32 is equal to 8. So the final answer is, how many columns were there? The maximum 8 columns are possible. We need to prove that square of any positive integer, neither odd is given nor even is given. Any positive integer square, it should be either of the form 3m or 3m plus 1 for some integer n. So m can be any constant number. So let us take, let a be any positive integer. As we are going to prove it is of the type 3m or 3m plus 1. So in place of b we have 3. So let us take b is equal to 3. So we know according to Euclid's division lemma, a was bq plus r. So this can be replaced as a is equal to 3q plus r. Because the value of b is 3, so r will be obviously greater than equal to 0 and less than b. That means it will be equal to 0, 1 or 2. Right? R cannot be 3. And now we will take different values of r to get what is a or what is a square, because we need to prove the square of any positive integer. So let us do it. So I have done, if r is 0, a will be 3q plus 0, that is 3q. So a square will be 3q the whole square, which is 9q square, which can be expressed as 3 into 3q square. Now taking any constant k1 as 3q square, we will get a square is 3k1. Same way you can take when r is equal to 1. So a will be equal to 3q plus 1, right? And so a square will be equal to 3q plus 1 the whole square. And this will become 9q square plus 6q plus 1, which can be written as, we can take out of these two terms, we can take 3 common. 3 into 3q square plus 2q plus 1. So we can again write it is of the form 3k plus 1, where k1 or k2, if you want you can give a different name, k2 is equal to 3q square plus 2q, right? So we have expressed as a square as 3k2 plus 1. Earlier it was 3k1 and here we get 3k2 plus 1. Same way you can take r is equal to 2. So a will be equal to 3k plus 3q plus 2 and again a square will be 3q plus 2 the whole square, which is equal to 9q square plus 12q plus 4. Again we don't have to see all the three terms, we need to convert it into this form. So from the first two terms we will take 3 common. So it will be 3 into q square plus 4q plus 4. So again, or even you can take from this also, 4 we can divide as, in place of writing this step we can directly write 3 into 3q square plus 3 into 4q plus 3 into 1 plus 1. 4 can be splitted in this way, 3 plus 1. So we can take 3 into 3q square plus 4q plus 1 plus 1. And so it will be 3k2 plus 1, okay, where k2 is equal to 3q square plus 4q plus 1. So again you got the square in this form. So earlier we had got 3k or 3k plus 1, okay. So thus it can be said that, therefore it is proved that square of any positive integer is either of the form 3m or it is 3m plus 1, and hence the result is proved. Like this you can prove many more results. Now our new exercise is exercise 1.2. As I have already taught you fundamental theorem of arithmetic, each composite number can be expressed as a product of its prime factor. So we are being given certain examples, we will obtain the prime factors. Let us see how. So let us take one easy example, 140. So we know how to factorize it, 140 divided by 2. In the same way, 2 into 35, 5 into 7, 7 into 1. So I can directly write 140 is equal to 2 raised to 2 into 5 into 1. So 140 is a composite number which is expressed as the product of the prime numbers. Okay, same way we can do others also. So I have just calculated and kept 3825 can be written as 3 into 3 into 5 into 5 into 17, which means 3 square into 5 square into 17. And the same way 7429 can be written as 17 into 19 into 23. So please see that this number is formed by the product of 3 prime numbers. Okay, let us do our next question. It is to find LCM and HCF by this formula. LCM into HCF is equal to the product of 2 numbers of the given pair. Okay, so let us find it out. Now let us see this example, 510 and 92. 510 is 2 into 5s are 10, into 3s are 30, 30 into 17 is 510. Same way, 92 can be written as 2 into 2 is 4 into 23. So 23 4s are 92. Now in your primary classes you have learned how to find out the HCF. Okay, before going to HCF we shall find out the common factors. So see, 2 is common here, okay, nothing else is common. So we will be writing here HCF is equal to 2. And same way, how to find out the LCM? The LCM we will write first the common factor 2, then the uncommon ones, that means 5 into 3 into 17 into 2 into 23. Means whatever is left out we will be writing one time each. Okay, so after multiplying these two numbers you will get the answer to be 23,460. Now if you find out the product, so we will be writing the product of 510 and 92 will be equal to 510 into 92, which will be equal to 46,920. And same thing can be obtained when we multiply LCM and HCF. So HCF into LCM is equal to the product of two numbers 510 into 92. So this will be 2 into 23,000 into 23,460 will be 46,920. So this result is already verified. Okay, either you can verify or you can use this formula also to find out the given LCM. Okay.